This video will give examples with limits involving infinity. Find the vertical asymptotes of the function. Let's say that our function f of x equals g of x over h of x. So remember that our vertical asymptotes occur where h of x equals 0 and g of x does not equal 0. So h of x equals 0 at the points x equals -3, -4, and 1. So now we can just investigate the points g at -3, g at -4, and g at 1. We know that g at -3 equals 0 because if we plug in -3 right here we'll get a 0. And at the other points it does not equal 0. So this tells us that our vertical asymptotes occur at x equals -4 and x equals 1. Now we're going to evaluate some limits. Let's see as x goes to infinity of x squared minus 100,000x. So you might be tempted to think that because 100,000 is so large, as x goes to infinity, we're going to get negative infinity as our limit. However, what really happens is that x squared, which has the higher power, dominates the entire function. So our limit as x goes to infinity is equal to the limit of the function just x squared alone, which very clearly we all know is positive infinity. And so similarly, if we take the limit as x goes to a negative infinity, we'll say that the x squared term still dominates, and so our limit is equal to negative infinity. Let's evaluate some more limits. The limit as x goes to infinity of sine of x. If we think about the graph of sine of x, we know that it's something called oscillatory, meaning it never really settles at one point. So this limit, in fact, does not exist, because you can go as far down to infinity as you want, but sine of x is still going to be oscillating, going back and forth. However, what happens if we multiply the sine of x by e to the negative x? Let's think. The limit as x approaches infinity of e to the negative x equals 0, because the graph of that looks something like this. So when you get to having really large x, what ends up happening is that you're essentially multiplying sine of x by 0, which of course ends up being 0. So our limit in this case equals 0. Find the horizontal asymptotes. If we're given functions where the numerator and denominator are both polynomials, then all we have to do is look at the terms with the highest degree. So in the first case, we're comparing something with degree 0 against something with degree 1. So the one with the higher degree, if it's on the bottom, then that means that our horizontal asymptote is 0. And this makes sense because as the magnitude of x gets larger, the magnitude of the denominator gets larger, and so we're dividing by a very large number, meaning that we're going to have something close to 0. Similarly with this function, as x gets very large, both the numerator and denominator go to positive infinity. However, the denominator, which is much larger, gets to infinity quicker, in a sense. So what happens is that we also have our horizontal asymptote at 0. Now, in this case, where the degrees of the polynomial are the same, then you have to look at the coefficient in front of them. So the coefficient of the numerator is 3 and that of the denominator is 1. So our horizontal asymptote occurs at 3 over 1, or 3. Find the slant asymptote. So the way we can do this is by rearranging our function using long division, something we all love very much. So I'm going to write this out. Now x goes into negative 3x squared, negative 3x times. So we're going to write that out. And so when we multiply, we end up with negative 3x squared plus 3x. So now when we subtract, we have minus 3x plus 2. Now we're going to divide one more time. That goes in negative 3 times. So we have negative 3x plus 3. And so now if we subtract, we end up with negative 1. So what this is saying is that our function can be rewritten as negative 3x minus 3 minus 1 over x minus 1. So now, if we think about the function going to infinity, what happens is that this part goes to 0 because the denominator gets very large, and we end up having this part dominating the function. So our slant asymptote is y equals negative 3x minus 3.